So how well can we do classically? What we can do classically is basically ask the oracle for a value. Ask for f of a, f of b, f of c. So how many do we need to know that the function is not constant? Anybody? Yes? N over 2 plus 1. Very good. N over 2 plus 1. Because, if you get the first one 0, the second one 0, the third one 0, all the way up to N over 2, 1, 0, they might all be, you might have been very, very unlucky and just chosen all your zeros, and then the next one, then the next one is a 1. So to know that the function is not constant, you need to ask an f of a where f is 1, and an f of b somewhere, or f of k where f is 0. So you need to get 1, 0 value, or 1 and 1, 1 value. And if n over 2 of them are 0, then it's not constant. You know it's not constant only when you've answered n over 2 plus 1 questions. And in fact, if you were playing a game with someone and you asked them, you were trying to guess whether a function they had in mind was constant or balanced, and they, and they happened not to write down the function beforehand, you would have to ask them m over 2 plus 1 to get the right answer. So classically, and how many queries did we, did I erase the quantum circuit? No. Well, this is the quantum circuit for the 2-bit case, but here's the quantum circuit for the n-bit case. And classically, we only made one call to the oracle. It was in a superposition of states that we called the oracle, but we only called it once. So we only asked them once. So quantum mechanically, the answer is 1. So this is much better than this. Of course, there is a drawback to how well can we do classically, which means that this paper really did not convince anyone that did not convince many people that quantum computers were better than classical computers. So anybody want to tell us this drawback? Yeah?
Wouldn't a randomized algorithm also just require an expectation of constant number of evaluations?
Yeah, exactly. Randomized. Ask random queries until you get f of I equals 0 and f of j equals 1. And this takes expected number of queries equals 2. Actually, it takes expected number of queries equal to 2 if you're really stupid about asking random queries and you don't check whether you've asked this query before. Because then the first query, well, we might as well assume it gives you 0. And then each additional query has a 1 over 2 chance of giving you 1. So the expected number you need to ask of additional queries is 2. So this is 3. So classically, deterministic, it's n over 2. Quantum mechanically, it's 1. And classically, if you have a randomized algorithm, the expected number of queries is 3.